Welcome to AI Paper Slop. We are diving straight into a paper from Baidu Inc. called Unlimited OCR Works. Welcome the era of one-shot long horizon parsing.
And if you are building multimodal models or, optimizing inference pipelines, this is one you really need to pay attention to.
Definitely. So here is the core insight you need right now. Imagine trying to copy a 40-page technical manual by hand, but you are physically forced to keep every single word you've already written actively loaded in your brain while you write the next one.
Right, your working memory would just completely freeze up.
Exactly. But for years, this is exactly what we've forced end-to-end OCR models to do. The standard multi-head attention mechanism forces the KV cache, which is basically the model's short-term memory, to grow linearly with every new token.
And then you blow up your GPU memory and your generation speed just completely tanks.
Yeah, but this paper fundamentally solves that bottleneck by introducing something called reference sliding window attention, or RSWA. It essentially locks the KV cache to a constant size.
Which is huge.
It really is. By pairing this with a highly compressed visual encoder, the Baidu team took a 3 billion parameter mixture of experts model and processed over 40 pages in a single forward pass. Zero latency degradation.
To really grasp why this is such a massive paradigm shift for ML practitioners, we kind of have to look at the ugly reality of the current industry standard.
The dreaded for loop.
Yeah, exactly.
Yeah.
Right now, long horizon parsing relies on this massive engineering hack. Models are forced to parse a multi-page document strictly page by page.
Because if they don't, they run out of memory.
Right, so at the end of each page, an external scheduler kicks in, abruptly wipes the cave and cache clean, and starts the next page completely cold.
Which completely fractures the context. I mean, if a complex table spans across a page break, the model just loses its structural understanding of the columns and rows, right?
Entirely. The goal of Unlimited OCR Works is to move away from that fragmented, isolated processing and actually emulate human working memory. When you or I do a transcription task, we don't actively hold every single word we've written over the last hour in our active recall. But we also don't wipe our brains every few minutes either.
Yeah, we retain the source material in front of us and we apply this sort of continuous soft forgetting to the text we just generated.
Exactly. And RSWA provides the mathematical implementation of that exact cognitive process.
Okay, so before we get into the mechanics of how they fix the text generation side with this soft forgetting, we really need to look at what is actually being fed into the system.
Because the encoder sets the stage for the entire memory footprint.
Right. The architectural foundation here starts with the visual input.
Yeah, and the researchers actually carried over the visual encoder from their baseline model, DeepSeek OCR. It's called the Deep Encoder.
And for the vision engineers listening, this is where it gets super interesting, because they aren't just using a standard vision transformer here.
No, they cascade two different architectures. They use SAM-VT and a CLIP-BIT.
Which makes perfect sense when you think about the two really distinct challenges of parsing a complex document. You need to know the layout and you need to know what it actually means.
You've got it. The SAM part, the segment.
Yeah.
Anything model that is optimized to understand spatial boundaries and layout geometry.
So it figures out where the columns are, where a figure ends, or, how a mathematical formula is positioned on the page.
Right. And meanwhile, the CLIP-PVIT handles the semantic meaning, the actual what of the image. So by combining them, the model gets both structural and semantic awareness.
But the clever engineering here is how they manage attention within that encoder to conserve GPU memory, right?
Yeah, they apply window attention to the original high-resolution image tokens.
Yeah.
That keeps the computations localized. But then they reserve global attention exclusively for the highly compressed tokens at the bridge between the two vision transformers.
We should definitely dig into that compression rate because it is incredibly aggressive. They achieve a 16x token compression rate.
Which is massive.
Right. In their base mode, which is designed specifically for multi-page documents, they take a 1024 by 1024 pixel PDF image and they squash it down to just 256 tokens per page.
Yep.
But wait, if they're compressing an entire high-resolution page down to a mere 256 tokens, why is there a memory bottleneck in the first place?
That is the big question.
If I'm an engineer looking at this, a footprint of 256 tokens per page seems completely trivial for a modern GPU.
It is so easy to look at that 256 token input footprint and assume the problem is entirely solved. But this highlights a major trap a lot of developers fall into when they analyze multimodal bottlenecks.
Which is what?
The visual tokens on the input side aren't the problem at all.
Oh, interesting.
Yeah, They are encoded exactly once during the prefill stage, and then they remain entirely static. The memory explosion is driven almost entirely by the decoding link on the text output side.
Ah, okay. So you have to consider the expansion ratio between a dense visual token and the text it actually represents.
Precisely. And the paper notes this expansion ratio is roughly 1 to 10.
Meaning one highly compressed visual token unpacks into roughly 10 output text tokens.
Right, because the LLM decoder has to do all the heavy lifting to unspool that dense representation into actual text, markdown, and all the formatting tags.
Okay, let's scale that up to a real-world use case for the listeners. Say you feed the model 10,000 visual tokens. Based on that compression rate, that is about 20 to 30 pages of a document.
Right, which sounds manageable. But to unspool that, the LLM has to generate over 100,000 output text tokens.
Wow.
And now apply standard multi-head attention to 100,000 tokens.
That's where the math just breaks down.
Exactly. The fundamental math of standard MHA dictates that the KV cache size, the memory storing the key and value vectors for every single token, is a function of the prefix length plus the generated length.
So your cache size equals the visual tokens, let's call it LOL dollars, plus $2, which is the number of generated text tokens.
And as dollars grows to 100,000, that variable just becomes monstrous.
Because standard attention forces every single new token being generated to attend to every single token that was generated before it.
Right. You end up multiplying 100,000 tokens by the embedding dimension, by the number of layers, by the batch size.
So your KV cache balloons into the tens of gigabytes.
Memory pressure spikes, the GPU literally runs out of SRAM, and your generation tokens per second essentially grinds to a complete halt.
Okay, so if the visual encoder is successfully compressing the input, but the GPU memory is still blowing up anyway, the math forces us to look at the other side of the equation.
Right, we have to stop that $2 variable from growing.
How do they actually achieve this without completely breaking the model?
This brings us to the core innovation of the paper. Reference sliding window attention, or RSWA.
Let's break this down.
So they took the standard attention mechanism across all layers of their 3 billion parameter mixture of experts decoder and just completely replaced it. RSWA splits the attention calculation into two highly distinct segments.
Okay, what is the first segment?
First, you have the prefix segment, which they denote mathematically as $. This segment contains all of your visual input tokens plus your text prompt.
Got it.
The crucial thing about the prefix segment is that it is globally visible to every subsequent token generated, and it remains completely static.
So it never updates?
Never updates. Its keys and values are computed exactly once.
It basically acts as the immutable ground truth for the model.
Exactly. Now, the second segment is where the magic really happens. This is the causal sliding window, denoted as nuller.
And this operates strictly on the decode region, right?
Right. Instead of a newly generated token looking back at the entire sprawling history of dollar output tokens, it is violently restricted. It only attends to the preceding dollar output tokens.
And what is the size of Noller here?
For this model, the default size for Nollers is just 128 tokens.
Wow, that is tiny. So going back to the analogy from the top of the show, this maps perfectly onto human behavior.
It really does.
If I am physically copying a book by hand, my eyes stay locked on the source text. That source text is the prefix segment $. It is globally visible to me at all times.
Right.
But when I'm actually writing the words down on my paper, I only glance at the last sentence I just wrote, like the last 128 tokens, just to keep my place, maintain my syntax, and ensure my grammar makes sense.
That is the sliding window dot.
Yeah, I don't need to reread the page I wrote an hour ago to figure out what the next word should be because the source text is still right there in front of me.
And the math translating that human behavior into GPU operations is incredibly elegant. Let's revisit that KV cache formula we talked about.
Okay, so with standard attention, it was $. plus.
Right. But with RSWA, the required KV cache size is $. Plus the minimum of line or 2 Rs.
Ah, I see.
Because Noller is a hard-coded constant of 128, the absolute maximum upper bound of your KV cache is simply $$ plus $.
So the cache literally stops growing once you hit token 129.
It completely flatlines. The cache is transformed from an endlessly expanding memory sink into a fixed capacity queue.
That is brilliant.
So every time the model generates a new token, the KV states for the oldest output token in that 128 token window are simply evicted and overwritten.
Which means as your generated length dollar scales into the tens of thousands, the memory footprint ratio of RSWA compared to standard MHA mathematically approaches zero.
Exactly. It completely decouples the length of the generated output from the hardware's memory consumption.
Now, that sounds great on a whiteboard. But if you're an engineer looking to deploy this, you are probably wondering how this actually compiles and runs on silicon.
Absolutely.
What does the kernel-level performance actually look like when you implement this in the real world?
Well, the researchers ran a kernel study using flash attention v3 to show exactly what happens at the hardware level.
And what did they find?
When you plot the per-call duration of the attention kernel for the baseline DeepSeek OCR using standard MHA, you see this climbing staircase. The latency scales linearly as the decode steps increase.
Right, because the cache is getting bigger and bigger.
Exactly. But worse than the linear growth, the graph is absolutely riddled with abrupt, massive latency spikes.
What actually causes those spikes physically on the GPU?
Those spikes are the result of hardware alignment boundary crossings.
Okay, unpack that for me.
So flash attention works by tiling memory. It pulls blocks of data from the GPU's slow, high bandwidth memory into the ultra-fast RAM to compute the attention.
Right.
But when your continuously growing KV cache crosses physical memory alignment boundaries, the data transfer efficiency drops abruptly.
Oh, I see. So the kernel stalls.
Yeah, it stalls and waits for memory access. It creates this jittery, totally unpredictable latency.
But with RSWA?
When you look at the exact same latency graph for RSWA, it is a perfectly flat horizontal line.
That's incredible.
Yeah, from token number 1 to token 6000, the per-call duration is identical.
So the inference framework is operating under constant tokens per second.
Exactly, completely avoiding those alignment boundaries entirely because the memory block size just never changes.
All right, for the ML practitioners out there looking to replicate this training run, let's look at the actual specs they used.
Yeah, the data engine was roughly 2 million document OCR samples.
What is really notable there is the ratio. 9-to-1 single-page to multi-page documents.
Right. And they trained this on a cluster of 8 nodes, each packing 16 NVIDIA A800 GPUs for a total of 4,000 steps.
They utilized the Atom W optimizer and the Megatron LM framework to handle the tensor parallelism.
Yep. And they completely froze the deep encoder and only trained the LLM parameters.
But the piece of the stack that really caught my eye was DeepEp, which they used to configure their expert parallelism.
Oh, DeepEp is critical here because of the context length.
How so?
Well, during the prefill stage, the model is still processing up to 32,000 tokens simultaneously just to ingest the visual pages.
Right.
Even though the decoder's memory is locked later on, processing 32K tokens through a 3 billion parameter mixture of experts model during training is computationally massive.
So what does DeepEp actually do?
DeepEp, which stands for Deep Expert Parallelism, it manages the routing of tokens to different specialized expert neural networks within the MOE layer.
Okay.
By setting the expert parallelism degree to 4, they efficiently distributed those massive 32K token activations across 4 different GPUs.
Which ensures that no single GPU runs out of memory during those massive matrix multiplications required to learn the global visual attention.
Exactly. It keeps the training stable.
Okay, so we've established the training environment, but we really need to talk about the evaluation results because this is where the paper throws a massive curveball.
It really does.
If we are literally throwing away the model's historical output down to a tiny 128 token window, the natural assumption is that the model is going to get lost.
Right, because soft forgetting sounds like actual forgetting.
Yeah. If you are parsing a 50-row financial table and you forget the header row, shouldn't the output just completely fall apart?
You would think so.
Yeah.
Yet the OmniDocBench benchmark results show the exact opposite.
It is so counterintuitive.
It really is. I mean, OmniDocBench evaluates not just simple text extraction, but complex formatting, mathematical formulas, and strict layout retention.
And how did it score?
On version 1.5, the Unlimited OCR model scored an overall 93.23%, which is a 6.22% overall boost compared to the DeepSeek OCR baseline, a baseline that had full access to its entire memory, by the way.
And on the newer version?
On the bleeding edge version 1.6 benchmark, it hit 93.92% overall, officially making it the end-to-end state-of-the-art.
Okay, wait, I need to reason this out. Specifically regarding the complex structured data, They reported that table TEDs improved by nearly 6%.
Yeah, table TED's the tree edit distance-based similarity metric.
Right, which measures how perfectly a model recreates the structure of a table's rows and spanning cells. And on top of that, the overall text edit distance actually dropped.
It did.
If it's only looking at the last 128 tokens, shouldn't it completely lose the structure of a complex table? Or, wait, does forgetting the beginning of the document actually prevent the model from getting distracted by irrelevant noise?
You hit the absolute nail on the head. That is exactly the failure mode of standard dense attention.
Really?
Yeah. Think about it. When you use full multi-head attention on a massive output sequence, say you are 50,000 tokens deep into a financial report, the model is still actively allocating attention weights to the title page, the table of contents, and a chart from 3 pages ago.
Oh, wow. In dense OCR, that massive historical context is mathematically totally useless for generating the current word.
It is worse than useless. It dilutes the attention weights. The model starts to drift. It loses its immediate structural placement within the current HTML or Markdown tag it is generating.
And that is precisely when it hallucinates a wrong column or merges 2 rows.
Exactly. It gets overwhelmed by the sheer volume of its own memory.
So by heavily restricting the sliding window to just 128 tokens, RSWA strips out all of that historical noise.
Yes, it acts as a strict, localized focusing mechanism. It forces the model to look only at the immediate structural vicinity, the current row of the table, the previous few words of the paragraph.
It keeps the state transitions tight and highly accurate.
Right. The model doesn't need to remember the table header from 3 pages ago because the global visual input, the dollar segment, is continuously telling it where it is on the page.
That is incredible. It is a genuine free lunch for AI architectures. Higher inference speed, vastly lower memory footprint, and demonstrably better accuracy.
It is rare that you see a win-win-win like that in machine learning.
All right, let's stress test the actual name of the paper. Let's talk about the Unlimited in Unlimited OCR Works.
Let's do it.
They took this architecture and pushed it beyond the standard benchmarks into true long-horizon parsing.
Yeah, the Baidu researchers built an in-house test set to see where the system would finally break.
And what did they feed it?
They fed the model tightly packed PDFs containing 2, 5, 10, 20, and 40-plus pages simultaneously.
And keep in mind, you guys, this is all happening in a single forward pass. No for loops, no external schedulers wiping the cache.
None of that.
And the metrics hold up under pressure. Even at 40-plus pages, the edit distance remained below 0.11. But the metric that really proves the architecture is working is the distinct 35 score.
Right. The distinct 35 metric is super crucial for long context generation. It measures the ratio of unique 35 grams in the output.
Why does that matter here?
Because when autoregressive models lose their place in a long document, their most common failure mode is falling into a repetitive death spiral. Endlessly generating the exact same phrase over and over again.
Oh, right, the hallucination loops. But the distinct 35 score here was 96.90%.
Exactly. The model didn't loop and it didn't hallucinate. It just kept continuously parsing and formatting fresh text.
But here's where the bottleneck shift gets really fascinating. At 40-plus pages, they did start to see an increase in errors.
They did.
However, the errors weren't caused by the LLM decoder getting confused or running out of memory. Based on their failure case analysis, the errors were purely optical.
And that is the ultimate proof of concept for RSWA.
Unpack that a bit.
Well, to fit 40-plus pages into the pre-fill context window, they were relying heavily on the deep encoder's base mode. And if you recall, that mode limits the visual resolution to 1024 by 1024 pixels.
Right.
So when you algorithmically pack 40 physical pages into that constrained resolution grid, the physical text in the image becomes incredibly tiny and blurry.
So the visual encoder simply struggled to discern the microscopic text on these tightly packed, multi-page PDFs.
Exactly. The eyes of the model failed, not the brain.
Which means they successfully took the limiting bottleneck entirely away from the LLM's attention mechanism and shifted it back to the visual encoder's acuity.
It is complete inversion of the traditional vision language model scaling problem.
Yeah, for years we thought the vision side was relatively solved and the LLM's context window was the absolute wall we just kept hitting.
And this paper proves the LLM doesn't have to be the wall.
But to keep things grounded, we do have to acknowledge the current limitations. True unlimited parsing isn't quite here yet.
Right, because of the pre-fill stage. The prefix segment, which holds those static visual tokens, is still bound by a hard context limit.
Because for this specific training run, the model was bound by a 32K context length.
Yeah, so even with a 16x visual compression rate, eventually, if you feed the model enough pages simultaneously, the sheer number of visual tokens will exceed that 32K preso limit.
So what is the roadmap? Where does the Baidu team take this next?
Well, in the short term, they plan to aggressively scale the training context length from 32K up to 128K. That will allow for much larger, massive pre-fill batches of visual data.
That makes sense.
But their long-term architectural plan is what should really excite developers. They want to build what they call a pre-fill pool.
Oh, how does that work?
Instead of loading an entire 500-page book into the prefix segment all at once, the model would be trained to automatically fetch and swap visual chunks from this memory pool as needed.
Wow. It would essentially simulate a human physically turning the pages of a book when they finish transcribing the current page.
Exactly. And they aren't restricting this just to OCR either.
Really? Where else are they applying it?
They explicitly state their intent to apply RSWA to audio speech recognition, or ASR, as well as real-time translation tasks.
Basically, any reference-based task where the source material is static, but the output generation needs to be continuous.
Exactly.
Which leads me to a final, really provocative thought for everyone listening to mull over. If RSWA can tame the KV cache for infinite text generation in a PDF parsing task, we might be looking at something vastly more important than just a highly efficient document reader.
Oh, absolutely.
Think about the current limits of AI agents. Right now, agentic systems hit a hard wall because their context windows rapidly fill up with the logs of their own historical actions and their chain of thought reasoning.
Right, they eventually just crash.
Exactly.
Yeah.
But if we now have an architecture that elegantly and continuously evicts its own past while perfectly maintaining its current operational state, maybe we are looking at the foundational architecture for continuous lifelong learning.
That is a wild thought.
I mean, imagine an embodied agent that can process real-time video or audio feeds 24/7 without ever needing an external memory wipe or hitting a hardware ceiling.
An AI that doesn't just wake up to process a single prompt and then terminate, but actually stays awake.
Yeah. It points toward a system that lives in a continuous stream of time, maintaining presence and focus exactly the way biological systems do.
It is a fascinating horizon for the entire field.
It really is. Thank you for tuning in to this breakdown on AI paper slop. We will catch you on the next one.